Hello, I, Shashank Agnihotri, am presenting CosPGD, an efficient white box adversarial attack for pixel-wise prediction tasks accepted at ICML 2024. This is a joint work with Steffen Jung and Professor Dr. Margret Keuper. DNNs are gaining popularity for estimating solutions to various complex tasks, including numerous vision tasks, as seen here, for example, optical flow estimation. For reliability, it is pertinent to know if the DNNs are learning meaningful representations or merely learning shortcuts to map inputs to the target distribution. Here, adversarial attacks play a key role, especially white box attacks that attempt to fool a DNN by optimizing an adversary using loss graded information from the DNN. However, most adversarial attacks are proposed to image classification, example PGD seen here. These do not utilize the pixelized information available. Thus, we present COS PGD, which leverages a simple alignment score computed from any pixelized prediction and its target to scale the loss in a smooth and differentiable way. CosPGD extends to all pixel-based prediction tasks and encourages a more balanced error over the entire image domain. CosPGD is an effective extension of the iterative PGD attack. Therefore, let's first look at the PGD attack. For an image X with ground truth label Y and model f theta and loss function L to generate an adversary for the next attack iteration or for the final inference, we start with the current adversarial example and take a step of size alpha in the direction of the gradients of the loss with respect to the adversarial sample. Then we clamp the adversarial noise to keep it within the permissible perturbation budget epsilon. And then we make sure that the generated adversary stays within the image space. Here, equation 1 considers loss L, which can also be written as the sum of pixel-wise loss L bar, giving us the following. However, as seen here, this does not take into account the pixel-wise information available. When optimizing an adversarial attack, our objective would be to fool the network on as many pixels as possible. Thus, it seems logical to focus the attack at fooling the network on pixels where it is more correct, while reducing the focus on pixels where the network is already sufficiently fooled. To this effect, we present CosPGD. CosPGD uses cosine similarities between the prediction and the target distribution to scale the pixel-wise loss such that for untargeted attacks on pixels where predictions are close to the target, the loss is scaled higher, while on pixels where the predictions are far away from the target, the loss is scaled lower. Vice versa is true for targeted attacks. We use softmax to obtain the distribution over the predictions. To obtain the target distribution, we again use softmax over the target in all cases except semantic segmentation. There, we will not encode the target. This helps to optimize the attack to fool the network on maximum possible image space while ensuring a smooth scaling. As seen from the plots below, this smooth scaling is indeed very important and is not ensured by previous work. Next, let's move on to some experimental results. Starting with semantic segmentation, here we observe that CosPGD outperforms all the other attacks across epsilon values and attack iterations. CosPGD encourages a more balanced error over the entire image domain, leading to a stronger and more effective adversarial attack. In case of optical flow estimation, we observe that CosPGD is able to expose previously unknown vulnerabilities of methods. For example, here, CosPGD is the only attack that is able to make the entire car disappear in merely 40 attack iterations. In case of adversarial training, we observe that CosPGD leads to a more stable adversarial training. For more details such as experimental results, ablation studies, and discussions, please refer to our paper. Link has been provided here. We also provide link to CosPGD code and sample implementation while also providing CosPGD integrated with segmentation. Please feel free to contact us in case of any further questions or doubts. Thank you for your attention.